Okay, welcome everybody. Welcome back from coffee. We'll continue our session on demographics and architectures. And to kick off this session, we'll have an invited talk by Eve Lee from UC San Diego. Take it away, Eve.
All right, just want to double check the mic is working correctly. Awesome, thank you. And thanks, Dan, for the introduction. And thank you to the organizers for this meeting and for inviting me. This is my very first Node iStar meeting. It's also my very first conference meeting since I moved back to Southern California as an associate professor in the brand new Department of Astronomy and Astrophysics. So it makes sense that I need to advertise because we're rapidly expanding. So for the junior members of our community in the audience, do keep us in mind as you look for your next positions, as you progress your academic career. So I was tasked to talk about the radius valley that we've seen quite a few times throughout this meeting, how evaporation plays a role, how other things play a role, as well as overall planet demographics and planet evolution. So that's a lot. So what I'm going to do is I'm going to couch this entire discussion in terms of overall star-planet interaction, focusing on small planet populations, so something that's smaller than Neptune. So we've seen versions of this radius gap plot for a few times, again, throughout this meeting. Size versus orbital period with a clear gap separating the two populations, the smaller rocky planets, the super-Earths, and the puffier planets, the sub-Neptunes. There are, largely speaking, three hypotheses to see how we can understand the existence of this gap. And the very first one, we've already heard the big picture overview on this hypothesis by Jesse. And we're also going to hear about this a lot more in detail on Thursday, I believe, by James Rogers. So I'm only going to touch like very, very little bit. So largely speaking, two modes or two versions of mass loss: photoevaporation on the left and core-powered mass loss on the right. The big difference between the two is the source of energy, as Jesse has explained. Photoevaporation, external source of energy, high-energy photons from the central star. The core-powered mass loss, internal source of energy coming from the heat of the core, or the internal heat. All I'm going to say is right now is that it's actually, physically speaking, really, really hard to shut off photoevaporation. So it is probably happening, and it is probably playing one of the major roles in shaping the evaporation or the radius gap that we see in the data. The second hypothesis is a compositional divide, where we all agree that the smaller population is rocky, but there's still some debate about the major composition of this sub-Neptunes. Either we consider them maybe they're water world, or they have the thick hydrogen helium dominated envelope. There's a very well-known degeneracy where just by having the size, mass, and orbital period alone, you actually can't really distinguish between the two. You need some extra data. And there have been some detections of what appears to be bona fide water world, but the jury is still out there because we don't know whether they are sort of the majority population or whether there's some small subset of the larger population of sub-Neptunes. And the third hypothesis is that this all comes from formation perspective before any sort of mass loss happens, whereby the planets, just purely from the initial gas accretion process in the later stages of disk evolution, you already have this bifurcation between the two populations. So because we're going to hear a lot about, in much more detail, about the mass loss later in this meeting, I'm going to spend a little bit of time on the formation part, and with the foregoing sort of thought that formation simply precedes any post-formation mass loss process. They never should be considered in competition, but it's more that it's simply just a transition of events. So why do we expect to see this bifurcation purely from formation? So this is a very classic plot in the exoplanet sort of planet formation theory dating back to 1996, and this plot still stays true to this day. So what you're seeing is the general growth of the planet, the mass growth of the planet, and initially the gas growth is rather sluggish, and this sluggish gas accretion process is due to the limitation by the cooling time. So the rocky core that is embedded in gaseous nebula, it will accrete and hold on to the gaseous envelope within its Hill sphere. But that accretion process is going to drive a non-zero temperature gradient. And as you all know, nature really does not like having any sort of gradient. So it's going to try to erase away that temperature gradient by cooling off that gas. And cooled off gas layer is going to shrink, which allows for this planet to build even more gas and accrete so that it fills back up its Hill sphere. So the rate at which such a planet can cool its gas layer and therefore build a thicker gaseous envelope is sensitively determined by how massive that planetary rocky core is, because it sets up the potential well. So the bigger the core is, the faster it is able to accrete, cool, and contract. So on this plot, I'm showing down to 5 Earth mass objects, but if you go down to even further lighter cores, say you go down below about 1 to 2 Earth masses, then the potential well is so light that there's just not much room to fill in that Hill sphere or Bondi sphere, such that you can pretty quickly erase away that initial temperature gradient. And once that gradient is gone, there's no reason for the gas to cool, so you're going to stop cooling, so you're going to stop your accretion. So if you account for that, then what's going to happen is when you calculate the expected gas mass fraction as a function of core mass, the final version, once the disk gas dissipates away, then this is what you're going to find. You're going to have a very steep exponential drop-off because zero temperature gradient means an isothermal layer, and isothermal mass is exponentially dependent on the core mass. And if you have this exponential fall off, then it's going to show up as a deficit when you take this and make a distribution of the size of the planets, which is exactly what we find. We simply take the theory and draw over a broad distribution of the core masses and figure out what is the size distribution you get out of. And indeed, you do get this gap in the radius space due to that isothermal drop-off. To the left of that, there's so little gas so that the size of the planet would be dominated by the rocky component, whereas to the right of it, you're in the cooling phase so that the size of the planet will be governed by the thickness of the gas layer. So these correspond to the sub-Neptunes. These correspond to the rocky Earths and super-Earths. So how does this look when we take a look at size versus orbital period? As a reminder, this is the data. There are multiple versions of this. This is yet another version. There is a gap, a clear separation between the two populations, with the slope of the location of the gap shifting down, so negative slope with respect to the orbital period. Now let's compare this to the theory purely from formation, and this is what we find. Clear gap separating the two populations, and the gap itself having a negative slope with respect to the orbital period. Why do we have this negative dependence on orbital period purely from formation before any sort of mass loss occurs? That's because as you go towards shorter and shorter orbital period, the disk gets hotter. That means it's going to be harder to accrete and hold on to those more thermally energetic gas particles. So that's going to shift down the overall isothermal maximum mass limit, effectively pushing to the right this transition between the cooling curve and the isothermal drop-off. So because the shift occurs towards the large core masses, there's a shift in the gap towards larger radius. This exact same physics will also give you a relationship, a positive relationship between the location of the gap and the mass of the host star. And in fact, you can do this more quantitatively to get an idea what exactly is that power loss slope, and it agrees extremely well with the data within 1 sigma error. And in fact, this all agrees with what you might expect from mass loss processes as well. So just from looking at the shape of the gap with respect to orbital period, just purely the mass of the star, you actually can't really distinguish between origin from formation, sort of primordial radius gap, versus evaporation. But as I have mentioned, it's really hard to shut off evaporation. So likely what's happening is that you can already get this gap purely from the beginning, but especially at short orbital periods, those planets will likely be further sculpted by things like evaporation. That means if you want to probe formation, the physics of formation, you do have to go to longer orbital periods. So go beyond 30 to 100 days or so that you are no longer as much affected by things like evaporation, because there the stellar insolation is rather weak. But as we all know, especially the observers, as we all know, we have much more data at short orbital periods because that is the easier places to detect and characterize the planets. So even though the short orbital periods may not be a great place if you want to probe formation, but that is an ideal spot to probe the physics of star-planet interaction. So for the rest of the discussion, I'm going to focus on short orbital period planets, and in particular, focusing on the edges and deserts that we see in the overall exoplanet demographics. So what you're seeing here, size versus orbital period, this is raw data. I have not corrected for any sort of detection bias here. It's not just because I'm just a mere theorist, but it's because I would like to draw your attention to the region where there is no data. Not because we have no sensitivity, but because those planets really do not exist. So we've already talked about this radius gap. Likely, you already have it at primordial stage, but at short orbital periods, it gets further sculpted by evaporation. If you look further up, there is a very clear cliff beyond around 3 to 4 Earth radii. We call this radius cliff, and Ann Dattilo later in this session will be talking about this. And to the left, you see no Saturn-sized objects at orbital periods less than around 2 to 3 days or so. We call that sub-Jovian desert. This sub-Jovian desert can be very well explained by photoevaporation. And that's because Saturns are large, so they present a larger cross-sectional area, but they're also lighter than the hot Jupiters, for example. So Saturn-sized objects are actually very susceptible to evaporative mass loss, especially this close in towards the star. Now, I think it's a bit hard to see with the lighting, but there is a protrusion over here, if you can maybe squint your eyes. There's a protrusion over here, and that is like a protrusion of very short orbital periods, ultra short period, rocky planet population. So what is creating this protrusion right over here? And how can we understand the edges, the shape of the edges of this protrusion? This protrusion, or the edges of this protrusion, also appears in different space, like in mass. And there has been a recent report that over a wide range of host stellar masses, there is a uniform maximum limit to the mass of the rocky planets, and that is at around 10 Earth masses. So here's one way to take a look at the data. The different panels correspond to the different host stellar masses, and you can see that there seems to be some uniform upper limit at around 10 Earth masses. Now, that seems rather conveniently close to what we typically quote as the critical core mass for the triggering of runaway gas accretion that gives us the gas giants. But as you will hear from Vincent Savignac on Thursday, the critical core mass is not always 10 Earth masses, and in fact, we would expect a pretty wide spread because it depends on the formation conditions. But perhaps more critically, we do see quite a number of sub-Neptunes which clearly have not undergone runaway with masses that exceed 10 Earth masses. So that's probably not what's shaping this uniform upper limit. But rather, what I'm going to show you is that this can come about due to a combination of complete stripping by photoevaporation and tidal orbital decay. So we're going to start with photoevaporation, and we're going to calculate what is the mass of the core below which the core is so light at that given orbital period that we expect the planet to completely lose its envelope over its system lifetime. And that's given by this blue line. The reason for the thickness of the line is because of the uncertainties in the ages of the host stars, or the spread of the ages of the host star. So if you're above that blue bar, and you see the planets there, that means those planets have retained some gaseous envelope. It is massive enough. But if you're below that line, then those planets are likely completely rocky. The shape of this makes sense because the further out we go from the star, lesser stellar insolation, easier for the smaller planets to survive. Also notice how the location of this blue region is quite constant as a function of the different stellar masses. And that is because even if the absolute value of the X-ray plus UV luminosity does increase with the stellar mass, at a given orbital period, the orbital distance also increases with the stellar mass, so they kind of cancel each other out. Another way to say this is orbital period is a pretty good proxy for the stellar insolation flux. Okay, so in this calculation, there is a fair bit of assumptions that went into this, but in spite of all that, notice how well it does in reproducing sort of the overall shape of this edge in these plots that we see. Now, what about on the left? So on the left, this is where we can consider the tidal orbital decay. So these planets already begin at orbital periods of about a day or so. So they're very close to their star. They are orbiting faster than the typical spin of the star. So the tidal interaction would lead to the loss of the angular momentum of the planet, therefore the orbital decay. And this is due to the tides being raised on the star by the planet. So that's given by the red region. Below the red region, the planets are light enough. They're so light that they do not cause enough tidal perturbation within the star. So these planets are more likely to survive because their orbital decay is rather sluggish. But if you're above that red line, then those planets are massive enough. They can undergo pretty rapid tidal decay, so that over the system lifetime, they will fall into this Roche-Lope region, the gray line, the gray zone, which is like a forbidden zone, and they'll be destroyed. And where these two lines meet, the red and the blue, is at around 10 Earth masses over a wide range of the stellar masses, exactly reproducing the data. Although the story seems a bit not quite in agreement as you look at the M dwarfs. And that is likely physical. It may be pointing towards the fact that the tides may be more efficient around M dwarfs. We don't yet have a good theory for the efficiency of the tidal decay, but this data may be suggesting that indeed we would expect more efficient tides for the cooler stars, and that is at least at a zeroth order that is expected because these cooler stars have a thicker outer convective layer. Okay, so if we go back to this overall picture of the exoplanet demographics, this is where the tides come in. Notice how it does a pretty good job at getting the shape of that edge right. Sorry, I'm not sure if you can see with the lighting, but I promise you it does a really good job at getting the edge. And you can also see that where the evaporation gap and the tides meet, that will give you this uniform maximum 10 Earth masses. Okay, now what about this edge over here? There is an innermost edge to this protrusion over here. And to explain that, we're going to consider yet another mode of star-planet interaction, and we're going to consider magnetic fields. Stars have magnetic fields, and as the planet orbits around the star, it's going to pluck along the magnetic field lines. And just like how we produce sound by plucking along like guitar strings, as the planet plucks along the field lines, it's going to drive waves, like the Alfvén waves. Furthermore, this perturbation, local perturbation in the magnetic field as the planet orbits around, it's going to create a time variability in the magnetic field. And you might recall from your E&M class, time-varying magnetic field will induce electric field. An induced electric field will drive potential difference across the planet. And again, nature really does not like having any sort of gradients. And that potential difference will drive current. So all of this occurs because the planet is perturbing the field lines and driving waves. And that wave has a finite propagation speed. So as long as the orbital velocity of the planet is smaller than the propagation speed of the Alpha wave, which we call the Alpha speed, there will be a causal contact between the star and the planet. And at this short orbital period, where you're at around a day or inside a day, that is always true. So that means there's sort of like a closed circuit with the planet and the star acting as resistors. And as we all know from our experience dealing with electronics in our modern day lives, resistance causes heating. There is a heat dissipation, which means loss of energy, which means there will be orbital decay. Again, especially because the planet is orbiting inside around a day or so, so it is orbiting faster than the spin of the star. We can write down this heat dissipation rate. That's how it looks like. It looks a bit complicated. It really isn't. So that term over there, that has magnetic field intensity, that is the magnetic energy density. It's the energy density contained within the magnetic fields, except the relevant component of the magnetic field here is the perturbed component. And that perturbation is like the degree of the twist caused by the orbit of the planet, which is the ratio between the orbital velocity and the Alpha velocity. So all of that together is the energy density contained within the perturbed component of the magnetic field, times the cross-sectional area of the radiator, the planet, and all of this is being propagated at the wave propagation speed, the Alpha speed. So with the heat dissipation rate, we simply let it equal to the time derivative of the orbital energy to calculate what is the size of the planet so that that planet, under this magnetic drag, would travel all the way to the Roche lobe and be destroyed over the system lifetime. And that is given by the blue lines. At the top, to the left, we're going to smaller and smaller magnetic fields. And it makes sense that with the smaller initial magnetic field, there's going to be a less magnetic drag, and therefore the small planets are more likely to survive. At the bottom, we're looking at lighter and lighter stars. This might seem a bit bizarre, but the reason why this happens is because unless the magnetic field intensity at the surface of the star scales really strongly with the mass of the star, the leading term for the magnetic field is dipolar. So at a given orbital distance, the lighter stars are also smaller. So the magnetic field decays a lot quicker. So that's why that happens. But the really important thing that I would like to point out is, compared to the tidal decay lines, which are the red lines, the fact that this plot, what it's telling you, is that for sub-Earth, ultra-short period planets, magnetic drag actually dominates over tides by quite a big margin. And that means these planets, even though they are small, they're actually cleaner probe of star-planet magnetic interaction, much more so than hot Jupiters, where it's a bit unclear because their dynamics is dominated by tidal decay. Furthermore, if you take at least like 0.1% of that heat dissipation and put it into the planet, pretty quickly you can destroy those planets. So these could be the progenitors of the catastrophically disintegrating planets that we observe. Furthermore, you can calculate what is the Joule heating rate of this, and that is actually on the order the amount required to drive the active volcanism that we currently see on Io. So maybe these planets are also undergoing volcanism. All right, so putting everything together, this is the magnetic drag line, and again, it does, given all the assumptions that went in, theoretically, it does a really good job at getting the shape of the edge of that protrusion right in the data. And So this was, I should just say this, so this was work done in collaboration with James Owen. I did all the analytic derivations. James did the numerical work. So if you go to that QR code, James made this nice video of reproducing that protrusion on YouTube. So do check it out. This is going to continue to show up. I won't get rid of it. So again, this magnetic drag, it's what dominates over tides for the sub-Earth ultra-short period planets. So that's all the theory, how we can understand these edges and deserts that we see in the current exoplanet demographics, especially at the shorter orbital periods. How can we further test this observationally? So I've already alluded to this, but for tides, we're still working hard to understand how tidal interaction scales with the different stellar type. The data seems to suggest that perhaps we really are seeing some evidence of more efficient tides for the M dwarfs. But if we really want to get this right, at a quantitative level, we need more mass measurements, especially because we need reliable occurrence rate measurements, not only in the radius space, but also in the mass space to do this correctly. Now, for the magnetic drag part, I think there are a lot of science cases that we can make. I've already talked about the star-planet magnetic interaction. This could be progenitors of disintegrating planets. It would be really great if we have more USP occurrence rate, especially for these small planets. Theory side, that actually depends on the conductivity profile, so we need a better conductivity profile within the planet. And for volcanism, this may be something we could probe with JWST if we can identify the atmospheric signatures from the outgassing from the volcanism, or maybe a thermal phase curve to probe the nice side. And finally, this line, even though it does well, the details does depend on the magnetic field evolution and the topology with respect to the stellar mass. So two ways to go about it. From the exoplanet community, again, we need the better USP occurrence rate, especially towards a wider range of the stellar masses, especially towards the extremes. Maybe TESS, Plato, maybe even Roman transit could help us there. And on the stellar side, we do need better probe of the stellar magnetic fields as a function of the stellar type. And I think I'm out of time. Thank you.
Wonderful. Thanks very much, Eve, for a wonderful talk. We have time for questions. Let's start in the front here. Stephen. As a reminder, please state your name and affiliation for the folks online as well.
Hey, Eve, great talk. Stephen Schmidt, Johns Hopkins. I'm curious about the magnetic drag, like what kind of time scale you would expect that to take for the USP planets?
Yeah, so this is the system lifetime. So it's on the order giga-year to 10 giga-year.
Okay, one question in the back.
Giga-year.
Hi, Tim Johns, Georgia State University. Other than white dwarfs, are there signatures in stars for planets in the process of being destroyed or for already destroyed planets?
Sorry, could you repeat your question?
Yeah. Are there signatures in stars for planets in the process of being destroyed or already destroyed planets?
Right, and then you were asking other than the white dwarfs that we have seen. Right, yeah, so there are actively disintegrating planets that we see, and we can see that in the transit through the cometary tails.
Okay, question on the left.
Hi, Eve. Jessica Libby Roberts, Penn State. I have a question about the M dwarfs. I know that as you get smaller and smaller in mass, your convective zone becomes larger and larger, and so it's sort of like a general transition until you become fully convective. I was wondering if you see any change if you were to plot this as changing mass.
Yeah, really great question. So if you take that upper limit to like 0.45 or like 0.3 instead, where you might expect a transition to fully convective zone, then actually, let me see if I can go back. Yeah, so what's going to happen is that instead of 10 Earth masses, it actually drops to around 4, which could be due to formation. And all of this goes away, and everything stops at 1 day. But for that, we couldn't really tell whether that was due to just lack of detection or whether that's physical.
All right, Belinda's next.
Hi, Belinda, University of Southern Queensland. When you say you want to know more information about the stellar magnetic fields, what do you want to know? What's the important thing? Is it the topology? Is it the field strength? Is it the variability? What is it that you've used in your models that you need to know?
Right, yeah, exactly. So I need both topology and intensity, how it varies with time, and how it varies with stellar mass.
Okay, so we have time for maybe 2 more questions. I think here on the left, yeah.
Steve Sauer, how does the field of the planet affect the SPI, the drag effect? How does the field of the planet affect?
Yeah. So we decided not to worry about it in this. We just considered it as like a ball of conductor. But yeah, that is our next step, to consider planetary fields.
All right, one last quick question in the front on card.
Hi, thanks for such a cool talk. Just a quick question about the M-dwarfs, because this is where you say that this effect might be the most interesting. We heard over the past couple of days how hard it is to characterize M-dwarfs, so we think we have a pretty good idea of their radii, but I'm just curious if you've thought about how the uncertainties that we have on some M-dwarf parameters like mass might play into the data that you're comparing these models to at all.
So are you asking about the stellar?
The stellar properties, I guess, like, are you drawing them here also just from the stellar, from the NASA Exoplanet Archive?
Yes.
And have you thought about maybe if the spread in the different ways that we determine those properties could affect what you're seeing?
Yeah, it will. It will. Like, short answer is it will. But like we are aware that like you cannot like always trust like just like what's on that table. You do have to be careful, especially for age. Like we really had to be careful. So for that, we actually went to another data set to pull off the age. But like that's a really good point. Like this does like you do have to be careful with like how much you trust the stellar properties that's like in the literature and collated.
Okay, let's cut it off here and let's thank Eve again.